Hey guys, this is Claudia, and today we'll be talking about titrations. So what is the purpose of titrations? Well, you're trying to find the concentration of a solution by mixing it with another solution with a known concentration. So let's say, for example, we have some hydrochloric acid and we have some sodium hydroxide. We don't know the concentration of our acid, but we do know the concentration of our sodium hydroxide. So if we know the volume of our unknown concentration of acid, then we can set up a titration lab and find that concentration. So when hydrochloric acid and sodium hydroxide react, the hydrogen ions and the hydroxide ions make water, leaving our spectator ions, sodium and chloride. Alright, so before you do any titrating, the initial pH of the acid solution should be very low because hydrochloric acid is a very strong acid, so it will completely dissociate, giving off a lot of hydrogen ions. Once the titration begins, the added hydroxide goes into the acid solution too and reacts to make water. An indicator that is added in the beaker before the titration occurs will tell you when you have reached your endpoint, or where just enough hydroxide ions have been added to react with all the hydrogen ions in the original acid solution. So as you're doing the titration, you should be tracking what the pH is as you add more sodium hydroxide. So the graph should look a little bit something like this. So like we said before, the initial pH is 0 because the hydrochloric acid is a very strong acid. So the only things in solution right now are hydrogen ions and chloride ions. So as we're adding more sodium hydroxide, it's reacting with the hydrogen ions in solution. And there'll be a point where there's only our sodium ions and chloride ions in water, because all of the hydrogen ions and the hydroxide ions have reacted to make water. So at the end point, moles of hydrochloric acid that was in the initial solution equals the amount of moles of sodium hydroxide that was added once we reach the end point. So that can be shown through the equation molarity of our acid times the volume of our acid equals to the molarity of our base times the volume of our base. The pH at the end point is 7 because all that's in there is water. The sodium and the chloride ions do not affect the pH because they're the conjugates of very strong acids and bases. So the pH keeps going up because you're adding more hydroxide ions. And at the top, all you have is your hydroxide ions in water. So what if you did the titration with a weak acid instead of a strong acid? You can set up the lab the same way, but there are some important things you need to note about a weak acid. What's very important to know about weak acid is that when it's in water, its conjugate base is relatively strong, so it will have an effect on the pH of the solution. So the titration curve for this example will look very similar to the strong acid, strong base titration, but there are several differences that you should note. First thing to note is that the concentration of our acid is greater than the concentration of its conjugate base, and that would be because its Ka value is far less than 1, which means that it does not make a lot of products. This also means that it does not have as low as a pH as hydrochloric acid. So we keep adding hydroxide ions, and by the time we get to the top of the graph, all there is in solution is our conjugate base and our hydroxide ions in solution. So now we're to the fun part. So we find our endpoint, which is in the middle of that sudden spike in pH. And what's interesting is that at the endpoint, which is the middle of that, the pH is above 7. And this is because at the endpoint, there's no more acid in solution. All there is water and our conjugate base, because all of our acid has reacted with hydroxide. And so, since the conjugate base actually is relatively strong, it will make the solution of a higher pH. Another important point on this titration curve is the half equivalence point. So if you find the volume of our sodium hydroxide it takes to reach the endpoint, if you go to where half of that volume is on the graph, then you'll have found the half equivalence point. At the half equivalence point, the concentration of our acid equals to the concentration of its conjugate base. So at this point, enough sodium hydroxide has been added to react with exactly half of our weak acid. So since the concentrations of our weak acid and our conjugate base are equal, this is also a point called the maximum buffer capacity. This is buffer because at this point in the titration, there is both the weak acid and its conjugate base, and they share a common ion. So if I add some kind of strong acid or strong base, and so for example, let's just say I added hydroxide, like we're actually doing the titration, our weak acid will react with the hydroxide to keep the pH about the same, which is reflective because at this point before we reach the end point, the pH doesn't change much. Another important thing about this point is that the pH of this solution at this point, at the half equivalence point, is equal to the pKa. And how come? Well, if you look at the Henderson-Hasselbalch equation, if our concentrations of our weak acid and our conjugate base are equal, when they divide by each other, it equals to 1. And so the log of 1 is 0, because 10 to the 0th power equals 1, or equals to 1. So that means the pH equals to the pKa plus 0, or the pH equals to the pKa. And so this way you can also find the pKa, and therefore the Ka of your weak acid. The reason why the strong acid would not make a buffer like the weak acid would is because its conjugate base is not very strong, it's in fact very weak. So it would not make an effective buffer. So titrations are not necessarily excluded to just finding the concentration of some acid. It can also go the other way. So here we have a strong base, strong acid, and it just kind of looks upside down, so that obviously the initial pH starts up a little bit higher, and then it goes down to a lower pH because you're adding hydrochloric acid. So like the strong acid, strong base titration, the pH at the end point for this titration is also 7, because at the end point, all you have is water and the conjugate acids and bases of strong acids and bases. So the same thing applies with the weak base, strong acid thing as it did with the weak acid, strong base. At the end point, the pH is lower than 7 because the conjugate acid of a weak base is relatively strong, so it will affect the pH at the end point. If there's one thing you should take from this podcast, is you must remember your indicator in the lab when you do titrations. If you don't use the indicator, you don't know when you've reached the end point, and then you have to redo the whole lab.